welcome everyone to this seminar. I'm very happy today to host Jukka Suomela. So Jukka is associate professor at Aalto University, and he's a prominent member of the distributed computing community. More specifically, his focus is on theoretical distributed computing, and even more specifically on the space side of things. So his most recognized topic is studying locality in distributed computing. And he has won a number of awards, including the Fox 2019 Best Paper Award. And today, his talk is maybe a little bit controversial, but I guess he will explain this better than me. Jukka, the room is yours.
Many thanks, Sebastian, and many thanks for inviting me here. So yes, today's topic is something that I very much enjoy talking about because I'm a lazy person and I'd like to outsource all of the hard work that we as computer scientists are doing to computers. So we can try to keep this talk also interactive. So if you have any questions, any comments at any point during this talk, you can you're free to unmute yourselves and shout questions, or you can type questions and comments in chat. I'm following also this Zoom chat all the time while I'm speaking, or at least I'm trying to. I hope all of you can hear me properly. If people in the audience, if you can turn on your video cameras, it will be really great. Of course, I understand that many of you would like to protect your privacy, but still, if you don't have anything secret in the background, if you can turn on your video cameras, it's much nicer to be talking to like actual heads instead of just black boxes. But okay, let's now actually get started. So we are computer scientists, and somehow the fundamental question in all computer science is what can be automated? And today's topic is basically the question of whether we can automate our own work. So I will now focus specifically on the question of automating the study of work in my own area, theory of distributed computing. And if you think about what people are doing in, let's say, in theory of distributed computing, a very typical example of what people are doing is something that you can see in conference papers in conferences like ODSI and DISC. And if you take a look at a random paper from ODSI or DISC or other conferences in the same area like Sirocco or PODIS and so on, let's stop and think about the following questions. First of all, how much of the work is usually done with the help of computers? I'm not talking about like people are actually using computers to typeset their papers in LaTeX. I'm actually talking about this real intellectual research contributors. And the second question is, well, if not so much is done with computers, how much of it could be possibly, potentially done with computers? Now, if you try to think about the usual process by which we are, like, let's say, producing research results, usually it goes a bit like this. We start with a question. Of course, there are all kinds of research questions that people are studying in thesis, but a very stereotypical question is something like this. You fix some computational task X. You fix some model of computing. In our case, you fix some model of distributed computing, N. And then you start with the question, is there an efficient distributed algorithm for solving this task in this model of computing? This is the starting point. And then how do you approach this? Well, I think usually it's roughly something like this. You find a bunch of smart people, then spend lots of time standing in front of a whiteboard, and then out comes something like an algorithm analysis, proof of correctness for this algorithm. Or in the case where the answer is no, you have, let's say, produced a lower bound proof that shows that this is actually not possible in this model of computing. I think this is what people usually do in the vast majority of cases that result in something like, let's say, whatever, Podsy disk publications. And now, today, what I'm talking about is replacing this hard part here in the middle, this part where you actually need smart people with computers. So, could we imagine that we just have a computer program where you can type in the description of your computational problem that you would like to study today, and then there are buttons like, please give me automatically a lower bound, please give me automatically an upper bound, and then you just this morning decide that, okay, today I'd like to do upper bounds. Let's click on button upper bound, and out comes a conference paper. Now, I think at this point, many people in the audience are probably already wondering if I have completely lost my sanity, because, I mean, after all, this sounds like something where obviously you will need human intelligence, and obviously our current artificial intelligence is like miles away from even having, let's say, mouse level intelligence, let alone like human level intelligence, let alone thesis researcher level intelligence, which is of course way higher than anything else. But I'd actually like to next give a toy example that demonstrates that in some settings, precisely what I was saying here is actually doable. I'd like to emphasize that I'm now giving a toy example that tries to make everything as simple and clean as possible. I'm coming back after this toy example to questions like, okay, what happens outside this toy example? But I think this toy example is already giving plenty of the flavor of the kinds of things that I'm really talking about. And as you're going to see, this is not at all about something like artificial intelligence or anything like this. This is just plain old algorithmics, but we are just switching to a meta level of algorithmics. So let me now give this toy example setting. I will define a model of computing, and I will define a family of problems. I will define an infinite family of problems, and I will then describe how you can automatically answer all questions about distributed computational complexity of any problem from this family in this model of computing. To keep things very simple, we'll just look at the case where our computer network is a cycle with n computers. And to avoid boring technicalities, let's assume that there is a globally consistent orientation. So our computer network looks a bit like this orange drawing here. There are these dots that represent computers, and then there are arrows that represent communication links. I mean, communication can take place in either direction. These arrows are just auxiliary information. Some friendly entity already gave us a globally consistent orientation that we can use to coordinate our work. And the model of computing is basically the standard model of distributed computing. Those of you who have heard about the local model, yes, we are working exactly in the local model, but no worries if you don't know the model. It's basically exactly what is described in this slide. So computation proceeds in synchronous communication rounds. In each round, all nodes can send arbitrary messages to each of their two neighbors. So one round is sending messages, receiving messages, updating your state based on the messages that you received. When I talk about running time, I'm talking about the number of the synchronous communication rounds, like the number of parallel rounds. No bounds on message sizes, no bounds on local computation. We just care about communication, how many communication rounds are needed. And we assume that nodes are already labeled with some unique identifiers. Think about something like IP addresses or something like this. So there are already some globally unique identifiers given that we can use to break symmetry, whatever. So all clear so far. So this is the setting. This is the model of computing that we are using in this toy example here. And then what kinds of problems we are looking at? We're basically looking at any discrete problems that you can define with local constraints. So we have got some finite set of possible output labels, and we have some kind of relation that tells which label combinations are correct. Let's look at concrete examples. It will be much more clear that way. Let's look at the problem of finding a maximal independent set. Independent set is a set of nodes that such that no pair of nodes is adjacent. And when I say maximal, I mean something where this independent set is not a strict subset of another independent set. And maximal independent sets are something that you can define using local constraints, because it is enough to just look at a window of length 3 everywhere in your cycle to check if what is given is really a maximal independent set. Here it looks good. Here it looks good. But here you can see locally that there is something that cannot appear in any valid maximal independent set. It is not possible that you have a sequence of a 0, 0, 0. Something is wrong here. And if you think about this, maximal independent sets are actually something that you can verify by looking at these these windows of size 3. And let's now generalize this idea. We are looking at any problem that you can define by looking at finite windows. So for instance, in the case of maximal independent set, it is enough to look at windows of size 3. And we can simply write down all possible label combinations that can appear in such a window of size 3. You can have 001, 010, 100, 101. And this is a complete list of all label combinations. So something is a maximal independent set if and only if all windows are from this set. If you see something else, you immediately know that it is not a maximal independent set. If you see only this, you know that it has to be a maximal independent set. So we can look at many other problems that you can define in a similar way. For instance, coloring is easy to define by just looking at windows of size 2. Here is also a somewhat random example of distance 2 coloring with 3 colors, which is something that you can also define by using larger windows. So we are looking at any problem that is of this kind of flavor, any problem where you can basically write down in a feasible solution, I want to see locally this or this or this or this or this everywhere. Is the setting clear? So basically, if you think about anything like coloring, maximal this and that, minimal this and that, basically any kind of like constraint satisfaction problem where you have some local constraints in your cycle, anything is coming from this family. Okay, any questions so far? So now what I'm claiming is that at least in this toy setting that I described, cycles and these locally checkable problems that you can define using basically a list of valid local neighborhoods. What you can do is you can write down the specification of the problem, like for instance, this specification of this maximal independent set problem that we see here. And you can feed the problem description to a computer program, and you can find efficiently both what is the distributed round complexity of this problem, and you can also find an asymptotically optimal algorithm for solving this problem. So we can have a computer program where you can literally type in this description and outcomes information, like the complexity of this problem is order of log star of n in this model, and this is a way to solve it in order of log star n time, and there is no faster algorithm for solving this. And this works for any given problem that you can describe like this. Yes.
Sorry, just not used of this notation. What is log star?
Right. So log star is the iterated logarithm of n, meaning how many times you need to iterate logarithm. How many times you need to iterate log function until you get down to 1. Or put otherwise, it's the inverse of power towers, basically.
Okay.
So and this is like log star. It's not very important for the purposes of this talk. It is, you could just think about like it is some function of n for now. But what you can see is that there are some non-trivial functions of n that can actually appear as round complexities here in this. And when I say you can find it efficiently, I mean that you can actually do all of this in polynomial time. Like the time is polynomial in the size of this problem description, where this problem description was just this list of possible neighborhoods that you can see. Okay, so how do you actually do this? So I will actually show the whole algorithm for doing this kind of decision. So how do we do it? We first turn our problem description, which is just a list of labels, into this nice graph representation. This thing that I'm describing here, this is a complex mechanical procedure. You can do it with pen and paper. You can do it with computers in polynomial time, nothing complicated. We just start with this list of possible neighborhoods that you can see in a feasible solution. You go through each of these one by one. And then you check which other neighborhoods are compatible. Like if one node can have this orange neighborhood, then we check what kind of neighborhoods its successor might have. So it is possible that I have a node that says this orange neighborhood. It is selected and none of its neighbors are selected. It says 0, 1, 0. And then one possibility is that its successor says 1, 0, 0. You just think about like if you're moving a sliding window, what you might see when you are switching by one step. So you might see either of these and nothing else. And we just construct a graph where, because this orange neighborhood can be followed by one of these blue neighborhoods, we just draw an arrow from orange to both of these blue. Very simple things. So you can turn this list into a graph. Nothing interesting happened yet, but these graphs are going to be much easier to understand than this plain list of labels. Is it clear how you can actually get this graph? Any questions at this point? Okay, now this graph is actually everything that we need. Now, from now on, we can imagine that instead of us being given a list of neighborhoods, let's imagine that we are given this graph, because this graph is easy to compute. So our graph for 2 coloring looks like this. Our graph for 3 coloring looks like this. Independent set problem is like this. Maximal independent set, if you draw the entire graph, it actually looks like this. And let's say this distance 2 coloring with 3 colors, it looks like this. So now we can start to look at these graphs and study their properties. Let's first look at this graph, independent set problem. Notice that I'm saying just independent set, any independent set, not maximal, not maximum, any independent set is fine. The problem can be described by using this graph. And now there is a self loop here in this graph. And it's very easy to say that as soon as you have a self loop, it immediately has to mean that the problem is trivial to solve. You can solve it in 0 time without any communication, because the self loop basically means that in this problem, there is a valid solution where everybody just outputs all zeros. So as soon as you see a self loop, you have a trivial problem. But it turns out that this is if and only if. Because if there is no self loop, you immediately know that this problem cannot be solved in constant time. You actually can prove that this problem cannot be solved in sub-log star time. So it is if and only if. A problem is solvable in constant time if and only if this graph representation happens to contain a self. Why is this? Well, if there is no self loop, then basically, if you look at any solution, you imagine you are moving a sliding window along this solution. Then at each step, you must be switching from one kind of a neighborhood to a different kind of neighborhood. So now if you, for instance, number these different neighborhoods with different numbers, you realize that actually what you are outputting has to form a proper graph coloring, because at each node, you have a different neighborhood. And then we know already from the 1990s that coloring a cycle requires log star of n rounds. So that's it. That was easy. So we know that as soon as there is a self loop, and if and only if there is a self loop, the problem is constant time solvable. Now let's look at something way more interesting, like this maximal independent set. There is no self loop, so we know already that it is not constant time solvable. Let's consider all nodes of this graph. And let's consider walks that start from this node and end in the same node. How can we walk in this graph? One possibility is that we take 1, 2, 3, 4, 5 steps and return back here. Another possibility is that we walk 1, 2, 3, 4, 5, 6 steps and return back here. Yet another possibility is that we walk 1, 2, 3, 4, 5, 6, 7 steps and return back to here. You are starting to see the pattern.
I just have a question.
Yep.
Why did you say 6 and not only 3?
Right. Very good. So what I'm trying to say here is that starting with 5, there is a self-returning walk of length 5, 6, 7, 8, 9, and so on. There is a self-returning walk of length 3, but not 4.
Okay.
So we cannot actually say something like for all numbers at least 3, there is a self-returning walk of exactly that length. But 5 is enough. So we actually have this definition. We say that a node is flexible if there is some value k0 such that there is a self-returning walk of length exactly k for all values that k at least k0. So this is the definition. So for instance, this orange state here is flexible. And at first, it's maybe not entirely obvious that flexibility is something that you can decide in polynomial type, because in some sense we are quantifying over infinitely many walks, but it is. So for instance, if you are lecturing about graph algorithms or something, it might be a nice puzzle for your students to figure out a polynomial time algorithm for classifying which nodes in a given directed graph are flexible in this sense. It can be done. It's not very difficult. So now the key point here is that once you are given a graph, then in polynomial time, you can figure out which, if any, of the nodes in this graph are flexible. And then it turns out that as soon as you can find any flexible configuration, for instance, this orange one, it immediately follows that you can solve this problem in order of log-Starring rounds. Why is this? Well, you can first use log-Starring rounds to find a kind of like ruling set type construction that is splitting your cycle in chunks where each chunk has length at least k0. So it doesn't matter if some of the chunks have slightly different lengths, as long as all of the chunks have length at least k0. You can do this in log-Starring rounds. One simple idea, if you're familiar with this Cole-Wishkin type graph coloring algorithms, then you know that in log-Starring rounds, you can find a coloring with constantly many colors. Then the coloring can be turned into an independent set, and then you can just basically amplify this independent set. So you find an independent set of independent set, and so on, maximal independent set of these independent nodes, and so on. You iterate this kind of construction until you have blocks that are long enough. Details don't matter, but the key point is that in log-Starring rounds, you can split your cycle in blocks. And then at block boundaries, you just put this orange configuration. And then between two orange configurations, you can basically just find a walk in this graph of a suitable length and fill in the gaps between the blocks. And that's it. So as soon as you have something that is flexible, you get very efficient algorithms. Not quite constant time, but very efficient. Logstar is a very slowly growing function. But now, I guess,
yeah. Maybe just a short question. So here, K0 is a constant.
Yes, yes.
So isn't it possible that K0 depends on n in some way?
Now, notice that K0 is a property of this graph that describes the problem. So once you fix your problem description, you have some finite graph with finitely many configurations. And this problem description is unrelated to n, where n is the size of your computer network. So
for coloring with square root of n colors, it's not possible to express it with your framework.
Yes. So we are really looking at here problems that have where you are labeling with labels from some finite set.
Okay.
So you really need to have this. I mean, technically, we are looking at LCL problems in this classic non-stop measure sets. So a very good question. So we are not even trying to express here anything where, for instance, your set of possible labels is all natural numbers or something like this. Good.
Okay.
So these problem descriptions are always finite objects.
Okay. Jukka, I'm sorry for a so basic question, but I misunderstood something because I don't see the self-return passes of 6, 8, and whatever. I see 5, 7, 9.
Right. So for 6, you can get by taking this 3 cycle twice. So,
yeah.
So if you can see my mouse cursor.
Sorry.
And 6.
So based, yeah, I'm sorry.
Yeah.
Thank you.
Okay, good. And again, for the purposes of the big picture, the details here are not important, but please feel free to also ask about the details if you are interested in this. But no worries if you, for instance, don't see what is this log start time algorithm. It's not important. Now, again, we had this implication in one direction, but it turns out that also in this case, there is equivalence. So if something is solvable, if a problem in this family of problems is solvable in logstar and rounds, then it actually has to imply that there is something flexible. And even more, if none of the states are flexible, we immediately know that the problem has to require linear time. So flexible means logstar time, very slowly growing function. If nothing is flexible, we immediately must have a problem that requires linear time. And why is this the case? Well, basically, if nothing is flexible, then it means that means something like, for instance, all self-returning walks must be even, or something like this. The lengths of all self-returning walks are something modulo something. So this basically means that if you consider two nodes that are very far from each other in a cycle, they have to output something. And now, if you imagine any, and furthermore, there are only finite many things that we can output. So there's definitely have to be two nodes that are far from each other that are outputting the same thing. And because this same thing is not flexible, we must be careful, because the solution is not completable unless you're careful regarding what is the distance between these 2 points where you are using the same non-flexible label. So the only possibility is that an algorithm is actually looking at up to linear distance before it commits to a given output. So problems are solvable in logstar time if and only if there is something flexible, and otherwise it requires linear time. And linear time is already the worst case, because in linear time you can gather full information about your entire cycle and by brute force locally solve it. So we're basically done. So you look at any of these graphs, you look at the description of any problem that you can describe in this formulas. If there is a self loop, you're done. You can output a trivial constant time algorithm. Otherwise, you check if there is anything flexible. You can do it in polynomial time. If you can find something flexible, you can easily generate a logstar time algorithm that is solving this. And this is going to be asymptotically optimal. And in all other cases, you can just output that, okay, sorry, the problem requires linear time, and you can basically output a brute force algorithm that is just gathering everything and solving it locally. You're done. So you can do exactly what I promised. You can take any problem from this problem family, you can feed it to a computer, and computers can efficiently in polynomial time print out, okay, here is now an optimal algorithm for solving this problem that you cared about, and here is its round complexity. Questions at this point?
Yes, does it generate the LaTeX source code of the paper?
Yes, I think that would be a nice exercise. Yes, yeah. But okay, now I think at this point, many of you are thinking like, okay, well, this was this top problem. Like, of course you can do this. Like, of course it's easy to solve this. But my point exactly is that in some cases, this automatic generation of optimal algorithms is actually it is not only doable, it is actually so easy that I was able to explain it here in whatever half an hour to you. So now, if you think about the spectrum of what might be doable, because in this case, things were so easy. So how far can we actually push the boundary? Can we do the same thing for a lot more interesting settings? Maybe not efficiently, but at least in reasonable time. And remember that we only need to do this once for a given problem. So maybe you can use a lot more computing resources and do something like this for way more interesting settings. And now let me briefly try to say a couple of words about like what happens if you step beyond this toy setting that we were discussing here. We were discussing cycles and paths. One natural extension of this is to look at what happens in, let's say, two-dimensional cases where your computer network is a grid, two-dimensional grid. Now, if you start to think about this and relate all of this to what we know about theoretical computer science in general, you start to realize that in cycles and paths, possible solutions can basically be something that is recognizable with a finite automaton. So in some sense, this case of cycles and paths is very automata theoretic, which is one of the reasons why we have good news. While the case of grids is already something that is, let's say, expressive enough to encode problems like execution histories of a Turing machine. You can even define a locally checkable problem that is basically of the form a feasible solution satisfies all the constraints if and only if it encodes the execution history of a given Turing machine. So now, as you can imagine, cycles and paths, automata theory, many questions are decidable even efficiently. Turing machines, many questions are undecidable. But I'd still like to give you some hope, because even if some problems are undecidable, it doesn't mean that there's no point in trying to solve those. So one of the tricks that we can use is the following. We can turn algorithms into normal forms in many cases. So it turns out that, for instance, if you're looking at two-dimensional grids, any algorithm that is doing something fast, let's say a log start time algorithm that is solving some local checkable problem, you can write it in a normal form. So in general, algorithms can do anything. They can maintain any kind of local state. They can do all kinds of local decisions. But you can replace arbitrarily complicated algorithms as long as they are fast and they are solving some locally checkable problem with a combination of two algorithms. One is fixed. It is finding distance k coloring for some constant k. And the other part is only using this coloring as input. It is not looking at anything like unique identifiers, random bits, nothing like this. It is just looking at this coloring that is produced in the first phase. And it is only looking at this coloring up to constant distance. So this second part is a finite mapping from distance something coloring to your final output. And it's surprising that any locally checkable problem that can be solved fast can be solved this way. Here fast means like something like logstar. And why is this the case? Well, very roughly speaking, the proof idea is that as soon as you have distance k coloring, you can use these colors as fake unique identifiers. And everything looks locally as if you were working in a very small network where you have small unique identifiers. And now we can basically just lie to our given original algorithm that we are actually working in a very small network, and these are actually globally unique identifiers. Just do your best here. And we can prove that if the algorithm fails, there is also an honest small input where it is going to fail. So this way, we can basically replace any logstar algorithm with coloring plus constant time operations. And now what we can do is we can just start searching for such a mapping. You go through all possible values of k, case 1, case 2, case 3, and we check if for any of these values of k, there is this kind of function b that maps distance k coloring into local output so that it is correct in all neighborhoods. And as soon as we find something, we can stop. Now, you may be worried about this part, like how do we verify that a given candidate function is actually good? But in some sense, no worries about this part. This is just finite amount of work. Once you fix a candidate B, it is a finite amount of work. So this is at least decidable. I'm not saying anything yet about complexity, but this is for a given fixed K and a given candidate B, this is a finite amount of work at least. So at least in principle, computers can do this. The real problem is that because the problem is undecidable, then somewhere we must have this undecidability. And this undecidability is hidden here. We can start checking values like case 1, case 2, case 3, and so on. And as soon as we find a K that works, we can stop. The problem is that if this given problem is not solvable fast, we don't ever know when it is safe to stop. But we can nevertheless be optimistic and guess that, okay, maybe this problem is solvable fast. Let's start checking case 1, case 2, case 3, as far as we can go with our computational resources. And if the search terminates before we run out of resources, we actually get an algorithm that solves the problem efficiently and is correct by construction. Now, the bad news is that somewhere here we have things that are doubly exponential in K, but nevertheless, the surprise is that what I just described, even though it seems abstract and horribly inefficient, this is still doable in practice in some settings, because one of the reasons is that many natural problems are often solvable with a small value of K. And we can also make this kind of approach way more feasible in practice. There are different normal forms that we can use. Instead of considering all distance K colorings, we can consider all possible ruling sets. A very quick back of the envelope calculation shows you that in local neighborhoods, there are way more possible colorings than there are, let's say, ruling sets, which helps a lot in terms of computational effort. And finally, we don't need to go through all possible candidates, but we can use things like SAT solvers to capture this notion of function B being valid. And we can use SAT solvers to find such a function if it exists. Again, the details don't matter, but if you look at problems like coloring a two-dimensional grid with 4 colors, now if you start to think about this, 5 colors is easy because it's kind of like a degree plus 1 coloring. You can just greedily pick colors of nodes in an arbitrary order, you never get stuck. Trying to do something similar for 4 colors is not so easy. And it turns out that the first explicit 4-coloring algorithm for two-dimensional grids that I'm aware of is something that we found using computer search. Exactly this idea that I described. Take normal forms and try to find a finite mapping that turns something like ruling sets into 4 colorings, and it works. It's very compact, and it didn't require in the end that much computational resources. Okay, that was just a detour to this case of grids. So to recap, we saw that in the case of cycle, yeah.
One quick question about the last slide.
Yeah.
So here you did transform, but the output is also a coloring. What was your input? It was distance 3 coloring or distance 2 coloring?
So here we were using this idea that instead of distance k colorings, we can look at kind of like distance k ruling sets. Okay. So if I remember right, the precise definition is something like maximal independent sets in kth power of the grid.
Okay.
And here this specific value of k was 3. So we started with a simple log start time algorithm that is finding maximal independent sets in third power of the grid.
Okay.
It sounds technical, but this is something that we know how to solve efficiently. And then we basically found a mapping that maps this maximal independent set in third power of the grid into 4 coloring.
Okay.
So this is the full picture here. Thanks. Right. So what I was saying is that we saw that cycles, automata theoretic, many things are easy, surprisingly easy. Grids, more like Turing machines. Many questions are undecidable, but it's important not to give up when you have an undecidable problem. It still may make sense to use computers because, for instance, in this previous case, as we saw, things are kind of semi-decidable. You don't know when to stop, but if you're lucky, or basically, if you happen to be lucky in guessing that an efficient algorithm exists, at least in principle, this search will then terminate and return an efficient algorithm. But and of course, this bad news regarding grids, they apply to any graph family that contains large grids as subgraphs. But now, what's between these two cases? Like, there is this very simple case of cycles, then there is this case of grids and anything that contains grids that takes us into this undecidable territory. But any suggestions? What's between here? What might be interesting graph families that are somewhere between these two cases? You can also type in the chat if you prefer. Trees. Yes. And more generally, bounded tree with or graphs with high girth, graphs that are locally like trees and so on. And it turns out that this is where we have got tons of very interesting open questions, because for grids, we have these formal obstacles in the form of undecidability coming from Turing machines and things like this. In the case of things like trees, we don't have any known formal obstacles. We cannot prove, we have not been able to prove that any of these questions would be undecidable. So it seems like there is a possibility that all of these questions that we have been talking about might be at least decidable. Maybe not efficiently decidable, but decidable in trees and beyond. And we already do have some positive results for the case of trees. I won't say anything about this, but if you're interested in hearing more about this, just ask me. By the way, just when it was last week, there was a new manuscript on arXiv that is exactly looking at these kinds of questions. Some specific setting in trees where everything turns out to be decidable. So now I think it's gradually time to start to move towards conclusions. So I will just say a couple of words about this kind of like big picture type questions, if there is still time. So in some sense, what we are seeing here is this transition from traditional questions that are about specific problems towards more meta-computational questions that are about the questions like, can we design a meta-algorithm where you can feed in problem descriptions and outcomes in algorithm that is solving this given problem efficiently? And these kinds of meta-computational questions are very closely related to questions about classification. So for instance, we already saw that in this toy setting that I was describing, we had an algorithm that classifies any given problem. But as a byproduct of this algorithm, we also got this result that any given problem in this problem family has to be of one of the three types. Either it is solvable in constant time, or it is solvable in exactly log star time, or it requires linear time. There are no other types. And in our field, we've got similar results way more in way more complicated settings. Like for instance, any locally checkable problem in general graphs is going to have a complexity that belongs to one of these 4 broad classes that I have illustrated here. And these kinds of classification questions are very closely connected to meta-algorithm questions. So basically, classification is understanding the landscape, what kinds of problems can be there, what kinds of complexities can be there, while these meta-algorithm questions are about figuring out for a given problem in which class it belongs to. And of course, these are very closely linked with each other because for instance, once you design a meta-algorithm, as a byproduct of the correctness of your meta-algorithm, you often also get classification. But I think now, looking at the time, I think now is a good time to stop. And I will just say,